All right, onward and upward. Looks like the next one here was talking about is clustered SCSI targeting using RBD. This was actually a blueprint submitted by Mike Christie. So Mike, if you want to give us an overview of what you're thinking, we can go from there.
Okay. I actually made some slides because I think, there's a bunch of SCSI stuff and it's difficult to explain. Do I just do the screen sharing thing?
Yep.
Yep.
Yeah, that's
okay.
good.
Okay, can you guys see them okay?
Yeah.
Okay. So I'm going to talk about clustered LIO or SCSI target support using RBD. I'm just going to quickly go over like the current state of HA support in Linux, and then I'm going to talk about our effort to implement active HA support, and then go over future work. Currently for the Linux open source HA SCSI targets, they all support active passive. There's a widespread pacemaker support for all the major targets like IET, TGT, and SAT, and LIO. With the pacemaker-based support, they only do node level failover. So when a node goes down, the passive node takes over. These implementations mostly rely on virtual ports. So for iSCSI, there'll be like virtual IPs on the active target, and when we switch over to the passive node does IP takeover. For FC, there's something similar called utilizing their virtual port infrastructure, and that's called MPIV. There's also some that are implicit OLUA failover based, and all that basically means is the target nodes will figure out when the initiators are not reachable, and they'll initiate failover from node to node. All the open source targets, they have support for single node persistent reservations, but a problem is that they don't have support for this kind of active passive node failover with persistent reservations. And so with that, what's needed is to copy that persistent reservation state from one node to the other. And there's some of them like LIO have interfaces for it, but there's no upstream support, no upstream tools. And like for SCSI, there's code, but I don't know if it's open source in the state of that.
So that means that the persistent reservations aren't actually persisted?
Yeah, in those active passive type setups right now, that's correct. They're not persistent.
And
it's actually pretty buggy. So when we switch over from the second node, the initiators expect that the device should be locked. There should be a reservation on it, and it doesn't exist. So you can end up with data corruption at worst.
Okay.
So
sorry, just one other question. Sorry, and you were talking the other day. I'm probably jumping ahead, but you were talking the other day about the SCSI compare and set thing that.
Yeah.
Oh no, that's what VSX is doing to do its own persistent, but that's the targets aren't doing that. So the targets aren't doing anything actually to persist. Okay, I got it.
Yeah. Okay. Yeah, I'll talk about more of that in the next slides. So this is just a picture just to give you an idea of like how active passive looks in that virtual IP type of setup. Like on the server, on the client, it only sees one path. There's two targets though, and each has a network interface and is exporting a path. But the client or server, it only accesses one target or gateway at a time through one or more virtual IPs. And in this case, there's only one virtual IP. The targets also have extra interfaces that are used by things like CoreSync and Pacemaker, and that's for like cluster membership and cluster-aware devices like DRBD. So DRBD uses it for its data replication. And again, if the target goes down, CoreSync and Pacemaker will be able to detect that, and it basically kicks off some resource agent scripts on the passive node to promote that node as active, and then also set like DRBD state to primary, so then the device is available on that secondary node. From server one's perspective then, depending on how long that failover operation takes, it might just look like a tiny TCP/IP blip, and so you might just have to retransmit some TCP/IP packets. If it takes longer, it might fire off some iSCSI or SCSI multipath timeouts, so you might have to retry iSCSI or SCSI commands, and at worst, you have to perform like iSCSI higher level recovery where you have to disconnect the old connection, reconnect, and then relog in. And in that, again, the multipath layer should handle that, and it retries the command. And so it's pretty simple. What we're trying to implement, though, is active-active HALL support. And the reason for this is, the main reason is that it makes it really simple for initiator support. With things like that implicit Lua failover, most initiators don't support that for boot, so there's just no way to support boot from it. And failover failback relies on the operating system's Lua stack, and a lot of times we found that's really buggy. And for things like Windows, it's extremely difficult to debug. And then also setup is just really simple. It just looks like a normal single node setup, and it just multipaths around the paths that are available. And so it's really nice from our perspective for support. Another reason this is nice is that we can support all the SCSI transports, so like iSCSI, Fiber Channel, SRP, and it's done in a common implementation. And there might be performance improvements, but it just depends on like where the bottleneck is in your system. So I got to test it. I don't know for sure. The drawback is, of course, go ahead.
When you're in an active-active situation, is it like sending IOs randomly to each target, or is it like, is the client going to flip back and forth when it sees one being slow? Or
yeah, it depends on the multipath. It depends on the operating system, and it depends on the multipathing layer. So depending on your multipathing layer and the operating system, you might have support for just like sending XIOs down one path and then doing the next path and the next path, or it might detect like latency, or it might detect like queue death, or there's like EMC's power path has different algorithms. So yeah, it depends.
Okay.
But yeah, and then was that all?
That's it. Yeah.
Okay. And the drawback and the reason that no one's done it so far is because it makes the target implementation a lot more difficult. For those active-passive implementations, there's no kernel changes that are required. It's just a matter of writing like some pacemaker and core sync resource agent scripts and writing some scripts to run some commands and copy data over. For the active-active, we actually need to modify the kernel to do like distributed error handling and setup and command execution. And so that's what I'll talk about in these next slides.
Okay, can we go back just one second for on the active passive slide, two slides back. The reason why active passive is problematic is because the targets don't persist reservations, I guess, but that could be presumably solved on the target side, right?
Yeah, that's correct.
What are the other sort of reasons why this is? Because I think you mentioned in stand-up that they're also just buggy on the client, on the initiator side. Is that something?
Yeah. So with active-active, I was saying it's the failover and failback is a lot simpler. When you're doing active-passive, the way that we approached it initially was using explicit Lua failover. And so basically with that, the initiator, the server, they would see all paths to all targets. And on the active path, for the active target, it would initially use those active paths. And if that target goes down or those paths become unusable, then it would need, in order to switch over to the passive paths, it'll send over this SCSI command called set target portal group. And for handling that, and when you need to transition resources from the active node to the passive node, there's timing issues and there's error handling issues, and then also just various implementation issues with going from different operating systems for how they handle various Lua commands and stuff like that.
So that's for Lua, but if you were doing the virtual IP thing, then
with the virtual IP,
issue, right?
Yeah, with the virtual IP thing, it's just more a matter of being able to failover fast enough without the operating system's error handler kicking in. And for those, for the most part, I think it should be possible to do it fast enough without higher levels detecting an error. But yeah.
Okay. But even if they did it also sort of depends on the guest too, like whether some, seems like my understanding is that some older, not guests, but clients, the operating system will, if it gets a timeout, it'll start going read-only and failing, and others will sort of retry for longer and then eventually pick up again.
Yeah, the thing, there's lots of different timeouts throughout the storage stack. So there's things like if you're using Oracle, if you don't fail over quick enough, then it's going to initiate its cluster failover on its side. And so that's going to switch over its nodes at the Oracle level. and there's those operating system ones that you mentioned, and yeah, so various operating systems handle the timeouts differently, and then there's different timeouts at different layers. So yeah, we're trying to avoid having to deal with any of those.
Got it, by doing the active-active. Okay.
This is just what active-active looks like with RBD. We have 2 targets, and they're exporting 2 paths. And from the server point of view, it sees those 2 paths. It's just going to send. This one is just using a service time algorithm. So, but I'll still round robin basically over both of those paths. This one too, we still have like those secondary NICs, and we're using them for Coral Sync and Pacemaker, and that's mostly right now just for cluster membership. But depending on how we implement PGRs and task management, it might be used for DLM and CPG too. I'll talk more about that in the next slides. And again, if this one for active-active, if the no goes down or paths to a no goes down, the multipath layer just marks it unusable and continues to use the other paths. And when the paths come back, it just marks them back online and starts using them again. So it's really simple. But again, yeah, the target implementation is going to be more difficult. So the next things I'm going to talk about for the implementation challenges are just the request execution and like synchronizing error recovery across the nodes, and then doing distributed setup. For the request execution, the one that you mentioned, compare and write, this is a SCSI command, and basically it just means to atomically read n bytes of data, compare them, and if they match, you write n bytes of data to some sector. The only known, and I guess mostly known user, is ESX, and in that it's known as ATS, or atomic test and set. And it's basically used for finely grained locking on their VMFS file system, or their clustering, or their heartbeating. And the default to you with this is if you're doing active-active on multiple nodes, and they're both executing the same request to the same sector, then we need some sort of locking to prevent one node from writing out data while one node is doing the compare. And so like today in the single node, it's just a normal kernel mutex per device that's taken whenever we execute this command. And so initially I was thinking I could just do translate that mutex to something like DLM, but it seemed easier just to push that execution down to the lower level device, so like RBD or DRBD or something like that, similar to how we do unmap and write same. And so I posted those patches, and I just need to still implement the RBD code for that. And also handle the upstream review comments, which are all doable. There's nothing really crazy in there. And so that's not really a big deal.
Was there a resolution on the item potency issue where if you have a failure and then you resend the command, you might get a failure, compare failure, because it actually happened?
For that one, we're just going to fail the IO directly upwards, and let the caller handle it. So for our case, LIO
so
will
would
just
have to reread.
Yeah.
Okay. And presumably ESX is smart enough to, if it does a failure on the compare and set, it'll reread it and see if it succeeded.
Yeah, ESX actually, it only does like a sector's worth of IO, and then actually there's some extra error handling information that's stuck in the sense data. It tells you exactly what byte didn't compare correctly. And it actually, we don't implement that in LIO for single node right now, and ESX doesn't really seem to care, and it doesn't really do anything super fancy when there's errors. It'll just retry and stuff like that.
Retry. Yeah. Okay.
Yeah, and so that one's pretty easy to implement. The more difficult one is the persistent reservation support. And basically, persistent reservations are just a bunch of SCSI commands that allow you to control access to a device. It's used by clustering software like Windows clustering and our RHCS. And they just basically prevent other client nodes from accessing the device. And they work by the initiator or client, whatever you want to call it. It'll send these PR requests to the target. And that tells them, in SCSI terms, it's called an IT nexus, but it's basically just ports on the initiator and target. And it tells the target what ports can access the device and what type of access they have. So like write exclusive or read write and stuff like that. And then this information, it has to be copied across the cluster. The initiators, the clustering software, it'll basically go across all the ports on the initiator and target and register them. And then I also want to be able to query them across through any port on the cluster. So We need all that information to be accessible from any port on the cluster. Then the ports that can be added and removed and the restrictions can be changed dynamically, but this mostly only happens at initialization time and the client node failover, failback type of time. So performance isn't really that big of an issue, which is nice. And so here's just like a basic example of how to do like an active persistent reservation. Initially, this server, it's going to send a PR registration command, and that registers the servers and the nodes ports, and it tells us to allow those ports to access some LUN N. Node 1 is going to store that information locally, and then it's going to copy that over to the secondary node. When that's done, node 1 will return a successful status for that operation to server 1, and the server will then repeat that for all the other ports on the initiator and target. Once all the ports are registered, it'll send the persistent reservation reserve command, and that's what actually establishes the reservation, and that's what prevents other server nodes from being able to access that LUN. And again, that information's like all copied across nodes, and when it's done, we return successful status to the server. And
so the persistent reservation actually says, I'm accessing this device via node 1 and node 2.
Yeah, there's lots of different combinations that you can do. Yeah, there's tons. Yeah. There's tons of different combinations you can do. You can tell that you're accessing it through a subset of the nodes, or certain nodes in that registration have access, and so it just depends on all the different parameters that they pass to the persistent registration and reservation command.
But it basically, the persistent reservation itself describes all of the paths in the multipath session.
Yeah, that combined with the registration information, it describes the paths that can access the device.
Okay, so I think in the RBD case, my assumption would be that we would persist those reservations as, probably the simplest thing would be to persist those reservations as properties of the RBD image. And so at time 2, it would actually write to the RBD metadata and say this is the persistent reservation.
Okay.
And then at time, whatever, at 5, where it repeats it on node 2, would it just verify that it's compatible, or would it say, oh, I'm adding node 2 to the set of things I can access this, or?
It's adding node 2 to the set of access.
Okay. Yeah. Okay. So it has like a shared cookie and says, I'm adding node 2 to the set of things that includes node 1 already, or is identified by some.
Yeah, exactly.
Something like that. Okay.
And so for the implementation solutions, that was the bottom one. The last one we were thinking about doing, just adding like some callbacks to the LL kernel modules, or passing the PR execution to user space. And so with that, we could call out to RBD and use like the Rados locking and the messaging. The other ones that are available are using like the crossing pacemaker DLM to distribute the persistent reservation information. The thing is, I guess people don't like DLM, so the pacemaker people were suggesting that we look into a crossing CPG library, which is just like a messaging library to be able to synchronize and talk to all the nodes in the cluster. And then another option that people are suggesting is the cluster, just have a cluster FS device that's used to store the PR info. Like currently right now in LIO single node, it'll store the information on a local file system. And so we could just make that a cluster file system. And So I've been looking into all of them. I haven't implemented this yet. Like at my old job, I did the crossing pacemaker DLM route, and it worked well. But yeah, so I just have to post patches to get everyone together on what people want for upstream. Unless someone has
Josh,
yeah.
I was going to say, Josh, do you have a sense of what makes sense for, I mean, my gut tells me that RBD already has this sort of messaging stuff that it's doing to coordinate snapshots and all this other stuff. So it's a little bit more work to like wire up the kernel interfaces to pass information down, but the tool's already there.
Yeah, I feel like it would be nice to just avoid using like external pacemaker things or coercing, like avoid having any of that set up, and just letting it be passed down to the RBD device directly, or maybe even pass through to user space and using the RBD there.
Okay. I'll try that route first then.
Actually, if we took that fourth route, if the LIO passed it straight down to RBD for the persistent reservation, do we actually need CoroSync and pacemaker at all then?
You might need it for task management, but I'll get to that. I've thought of another way to do it without CoroSync and CPG. So yeah, you might not need CoroSync or pacemaker at all. Well, but you would need it for like cluster membership for those iSCSI target gateways.
Just to configure them and.
Yeah.
Okay.
Unless there's like another method that you.
Okay.
So I'll look into the RBD-based way to do it.
Cool.
The second distributed type of request we need to do is that task management. Task management is just SCSI's terms for error recovery commands. And so like when a command times out or a device gets jammed up or wonky, the operating system will still send like these SCSI task management requests to abort commands, reset devices. If it gets really bad, then they'll reset connections or reset targets. The ones that we're most concerned about that'll be difficult for active-active is this SCSI device reset request. It's called like LUN reset in SCSI terms. And there's specific behavior that has to be followed for that. You have to abort all the commands on all paths on all nodes. You have to terminate all the other task management functions that are running. And when the reset is successful, you have to send basically a SCSI event. We call them unit detentions through all the paths that were accessing the device. And that indicates that the device was reset to the initiator and it can take some sort of error handling.
That's a command that goes out. That's like an up call that says, here I am, I reset. Okay.
Yeah, depending on the transport and implementation, it could be sent asynchronously through like, for iSCSI, there's an async event to do this. But normally when the first command comes in on a path, the SCSI layer will put that event or error information in a SCSI sense code and return the command to the initiator, and then the initiator will see that it's just a unit detention and handle it and then retry the command. So, and for this one, I tried to make another picture to hopefully explain a little better. In step one, the server, it doesn't know what happened to the state of the command. So to get the device in a known state, it sends that LUN reset. Node 1 will begin to process it. It initially blocks new commands, and then it starts to abort running commands. It also tells Node 2 to begin the distributed reset process, and so it should block and clean up commands. When that's all completed, we'll send a notification to the server that it's successful. And then again, on both those nodes, we'll send that unit attention notification through all the paths that were accessing the device to tell the initiator or the client server, whatever you want to call it, that there was a reset done and those commands were failed. And there's more details to that. There's different settings to be able to, sometimes you'll actually send failures for each command. Sometimes you don't. It just depends on the SCSI settings that are used.
So I think that would be pretty easy to implement with the existing messaging stuff that we can do between RBD clients.
Okay.
They could abort their commands and they would send the unit attention thing up. The question I have though is what would happen for an in-flight IO? Like say there was a write in progress when you did that reset, do you have to block until that completes or errors out? Or otherwise you have sort of an in-flight thing, a write that still might, it would, yeah.
Yeah, so right now, so you can have like, we call them task sets, and they're basically like a list of commands, and you can have it at the device level, or you can have it per path. And with those task sets, you can have like serial numbers and like task tags and stuff like that. And so when like a SCSI initiator would send a logical unit reset, it'll tag it with a serial number, a sequence number. And the iSCSI target will know that it should only fail all the commands before that sequence, before that reset. Okay. And so at the target level, it would have to be a combination of target and RBD, where the target level sort of quiesces the queue and makes sure that only the commands that are sent to the lower levels are failed, and it would make sure that some of them are properly handled and some of them are executed like normal. And so it would basically order them based on those serial numbers and stuff like that.
Okay. I'm just thinking what would happen if, let's say one IO hanged for some reason. So say it was sent to node 2 and it was doing a write and the RBD write wasn't completing for whatever reason. Maybe the backend cluster is slow. Maybe there's a bug or something. And so you send a LUN reset. Node 1 or node 2 they could either say, okay, I'm canceling the command, and they just ignore the fact that there was a write in flight that they haven't gotten a reply to, in which case you might complete the reset and then you read the same block from node 1, see the old content, and then somehow that write completes on the backside.
Yeah,
like
so
that's what's not allowed, right? That's what
Well, for SCSI, actually, so I guess this is sort of being debated with the target people on the list, or it was internally at my old job. And basically the argument is that if the SCSI target or device doesn't return a successful status to the client, then the status of that command, it could be completed, partially completed, or not completed. And the initiator needs to take proper recovery actions. So yeah, it's okay that it completes, even though we tell them that the reset, but if it completes, it's okay. So basically, we can't complete the LUN reset with a successful status and still, yeah.
Okay.
And so that's
okay. So I guess in that case, sorry if I just following this thread through. So if the node 2 then failed to reset, it just timed out doing the reset because it had that outstanding write and it didn't know what to do with it, then the client would say that the LUN reset failed on that particular path, and then it would probably change its SCSI reservations to like kill that path.
It would actually, it depends on the operating system, but all operating systems they'll initially try to abort the command. If that fails, they'll try the LUN reset, and then if that fails, they might do a target reset, or they'll try transport level recovery, and for that they'll for iSCSI they'll kill the connection, or for fiber channel they'll log out, and then they'll try to relog in and reestablish connections. And when you do that, it has certain clearing effects on the commands, and so that means like all the commands are supposed to be aborted, and yeah. So and then depending on how the relogin goes, then the initiators might take different actions.
Okay, so I guess the thing I'm getting at is that we have a fencing mechanism that we can use in RBD, but as long as there's a specific thing that we can use to trigger it. So like if the LUN reset failures and whatever the client action does to like change the reservation, if it's explicit about the fact that I'm removing this person from the reservation because they couldn't reset, then we can use that to trigger the fencing.
Okay.
But if they're just like saying, I couldn't reset him, so I'm removing him, but you don't know that it's because they're misbehaving, then we wouldn't know whether to fence.
Yeah, we don't know
why they're doing that.
Yeah, the thing is right now the error handler in like I think all open source targets is really dumb. All it does is when it gets like these aborts or resets, it just waits for the commands to complete. So it doesn't do anything right now. And so if the device is really hung, then it just ends up failing, and then the initiator escalates. Yeah. So.
Yeah, which I think it's probably what we want to do, and that's probably okay as long as we then know when to fence it. Right.
Yeah.
We also have to be a little careful with the fencing mechanisms we have, because it would only work if we were using the no-share option for the kernel module, so they wouldn't be using the same client for multiple RBDs. It's based on the client right now.
Yeah. Right. That's a little tricky too. Okay. I'm gonna just make a note. Need to figure.
Okay. I can probably just skip this next slide. So I was initially looking at that CPG stuff, but then I started to go the direction that you were talking about. So I was going to add, like currently right now, there's no way to abort IO, and there's no way to like reset a queue in a common block layer way. Like SCSI layer has functions to do it. But I was thinking like we could add like abort function and reset functions on the queue, and then LIO could just call it to tell like RBD to do like abort or reset, and then it could do its thing. So that's just basically what we just talked about. The only thing I would need though still is for when the reset is complete. So like on step 3 here, if the reset comes in through node 1, I need a way to tell node 2 that its commands were failed due to a reset. And so I can, yeah.
I think we have that. I think the notify stuff that we have already. So node 1, and correct me if this doesn't make sense, Josh, but I think node 1 would just send a notify message to the image that says reset. Node 2 would receive that and block until it receives all the acts, and then acknowledge the timeout, acknowledge the notify.
Yeah, that makes sense.
Okay.
And so in the successful case, then those IOs complete quickly, fast enough that the reset can then complete in a timely manner. And in the bad case, those requests are hung and it fails to acknowledge the notify. And so node 1 gets a notify timeout, and it will say, I failed to notify, or I failed to do a reset. It'll fail to reset. And then the client, presumably the server initiator, would say, which ones have I seen a sense from? And I assume those ones are working, and the ones that I didn't receive a sense from for the bad ones, and I'm going to remove those from my multipath.
Yeah, basically it's something like that.
Yeah. Okay.
All right, that sounds good. Yeah, that makes it easier for me than in the target layer. Okay.
Yeah. It's a little bit more work in RBD, but I think we have all the pieces there.
Yeah.
So, yeah.
The only other thing I had was management. I haven't really looked into this in the implementation details. I was hoping to there's like this remote configuration daemon called target D that we implemented at Red Hat, but the maintainer just wants to keep it really simple. So for clustering support, I'm not sure where to add it yet. I've just been manually setting things up. But so yeah, I could add it to like the LO RTS lib or write my own or something like that. I basically just need to distribute like UUIDs and SCSI settings and set up devices and things like that. And then also we need a way to support external interfaces like VMware's VASA and Oracle's and Red Hat's libraries. Yeah, and I haven't really looked into this a lot, except for...
So for those external interfaces, those are consumers of this API, or this is calling it? Okay.
Yeah, the ones like VMware VASA, they would be interacting with this lower level library that does the Linux specifics. And then those like tools based on VMware VASA or Red Hat storage management interface would go through those interfaces, and those interfaces would then talk to this lower level like LIO or target D1.
So, I mean, it seems like there are a couple things you could do. You could make a Ceph RBD specific one that's like RBD target agent D or whatever, that knows nothing except how to set up targets, and that handles the sort of the clustering thing. And that could be coordinated by, configuration state that's stored in Ceph or via some API. I think the other thing we could do is we could wrap this into Calamari itself. Have it do sort of the same thing, although I'm not. Okay. It might as well just live in its own piece. Or I guess the other path would be, want to make something generic that's generically able to orchestrate, multipath gateways.
Yeah.
Targets. In which case, it seems like target D is the right thing, or something like it, right?
Yeah. Yeah, it's a simple implementation detail, so it's not a big deal. It's just like a lot of work, so I just need time to do it. But,
yeah. So the target D is like a single node.
Yeah.
Type of thing. Is it like a REST API or something, or what is it?
Yeah, it uses RESTful API.
Okay. On a single node, it sets up a single path target.
Yep.
Basically.
Well, it could be multiple paths on that single target, but yeah, single target.
Got it. Okay.
That's all I have.
What if you had target Ds on each of the different target hosts, and then you had something that was consuming those target Ds? Would that be sufficient? Like if Calamari was talking to a bunch of target Ds.
Yep.
To set up the.
I believe that would work. I'm not really familiar with Calamari, just like the basic.
Yeah, I'm not either. I'll be honest. But okay. But there's some shared state somewhere. I mean, what is the? It's basically. So it's the UID of the target, what image it maps to on the back end, and knowing what the cluster of targets is going to be.
Yeah.
Sorry, it's the UID of the LUN, the cluster membership for all the targets, and then what image it maps to, basically.
There also might be other information like, well, you got to do things like will you ever want LVM over RBD or things like that? Or would you rely on RBD type rate and plus volume management? Or
I think I'd probably use the RBD snapshotting stuff, but not LVM. I don't know what LVM would really buy you. Yeah. I mean, I guess you could, but.
So we're about 10 minutes over. I don't know how much more you want to dig in here.
Well, we have until. Oh, we are over.
Yeah.
Oh, yeah, we are. Oh, wow. Wait, I'm totally confused by this timestamps. No, we have until 3, right?
No.
Oh, unless if we
2:30 was when you were supposed to start on the checksums.
Oh, because you shifted the schedule. Aha. I keep not reloading the page. Got it. Okay. Okay, so I guess the last question I have, and this is actually a question for Jason and Josh, I guess, is this is in the active scenario, there are going to be 2 targets that are have the same RBD image open and are doing synchronous I/O to it. So is that gonna map onto the mandatory locking?
So there's that new image watcher functionality that's part of the exclusive lock, and it's not necessarily tied to exclusive locking. You can send any number of messages over it, because the lock is just something that you can take in addition to listening to all these notify messages. So you could add it onto that, or you could just make a brand new like watch notify mechanism on an image. Just depends how you want to take it.
Okay. I think we just wanted to disable apply these images that would be used in because these set up as shared, so they wouldn't use any of the locking stuff for RBD locking. Okay. Since
all right, okay.
The target layer is managing that.
Yep.
But we could use the same infrastructure that like Jason wrote for that to handle the notify things that we wanted to handle.
Okay.
Yep.
And one of them would just be randomly elected the leader or whatever.
Well, you wouldn't necessarily.
You wouldn't even need to have a leader.
You wouldn't necessarily need to have a leader because you get peer-to-peer messages. It just depends how these SCSI things.
When you take a snapshot, it'll sort of use the old behavior where it sends a notify to all watchers.
That for the header update versus the please do the snapshot.
Yeah.
Yeah, I guess so.
Okay. I just want to make sure we contemplate this because this is sort of will be one of the main features for the kernel RBD lock device, and it's not the sort of the typical single client thing that we also want to streamline.
Right.
I guess it seems like in the general case you ideally want the when you just do RBD map with like no extra flags or whatever, it'll just implicitly do the exclusive locking or give you back an eBusy.
Yeah, I think we were thinking that the exclusive locking would be a feature bit basically, so it would be enabled on the image or not. So if you map an image with it enabled, then it would handle it.
Got it. Okay.
Exactly. Yeah. The CLI, when you create the image or import a new image, you basically tag it as shared at that point in time, which at this point in time disables that feature.
Would it make sense to say shared with this lock ID or whatever, and that would be the UID that the targets are using? So it's like this specific set of targets essentially are the ones that are going to be the ones that are owning the lock stuff? Or is that too convoluted?
Yeah, I'm not sure what that would really add much value.
Yeah.
I could just confuse things.
Probably. Okay.
But yeah, we have to make sure that the snapshot and other kinds of management paths would still work in this scenario.
Yeah.
But I think if we just basically treat it as an old style image, that it would make sense. Just have the command line tool that's doing it, do the operations like usual, and notify the kernel clients later.
The way the code is structured right now, it basically says it won't try to proxy it unless it says is the exclusive lock feature supported, and then try to get the lock. If you can't get the lock, then tunnel it.
Then okay. Cool.
I had a question. Is there any way to detect if oh no, never mind. I was trying to think of a way to not use Coral Sync and Pacemaker since we're not using it for any of those other IO related things. But is there any type of generic cluster services that Rados or Ceph provides that I can just
kind of. So you can store whatever you want in Rados, right? So you could build something up without too much trouble.
Okay.
For a given image, you can tell who has it open effectively by looking at the list of watchers. And then you can send messages to those watchers. I'm not sure that that's going to give you everything that you need though on the orchestration side, like setting up the target stuff. Like I think you'd want to do that because that happens before they actually have it open. It seems like the thing that makes sense to me is that you get these persistent reservation commands and you translate those into Rados class operations on the RBD header that say set this persistent reservation or get the reservation state or whatever, and do that exchange inside the RBD kernel driver, essentially. And then I guess there's a get reservation command also that'll pass that data back up. Okay, so we would pass that back to the client, and the client would decide how to react to it or whatever. And that might be, I think that the thing that I'm not sure about that I'm hoping is the case is that if you identify which path is not resetting, that when you go to break the reservation, it's somehow explicit so that we know that we should fence that person.
Yeah, there will be commands to on other paths to tell us like kill the other registration and abort commands and various ways like preempt other registrations and preempt other reservations, and so that gives us some information.
Okay. So like in the normal path, you would use path A to remove path A's reservation and path B to remove path B's reservation. Maybe.
There's lots of.
But if you did it from the wrong path, it would know that it's a reset or something like that.
It's based on everyone has decided to do it differently, and so that's why no one has implemented it.
Okay.
It sounds like we still need it to be like a user space pass through thing for these reservations, unless we wanted to plummet all the way down to the block layer, because there's no like generic block layer handling for this kind of thing, right?
Yeah, that's correct. And I can pass those to user space. It should be okay. I can just when we get those in the kernel, we just pass them up to user space and.
Okay. I think in that case, then we would need an agent, like a RBD agent that's running on the thing that also has librd with the same image open from user space.
That's okay then to have user space open it and then kernel space open it and
Yeah.
It's a little bit weird because you have two clients from the same host to whatever. I mean, but
it's a little strange for the user space one is just for management and handling these extra watch notify things.
Yeah. Okay. Cool. Okay. I guess we can wrap up.
All right. Mike, if you could send me your slides, I'll get them posted up on the wiki too when I post the videos.
Okay.
Thanks. Awesome. All right. Thanks.